In this lesson, we will learn about the extreme value theorem. And what that involves is giving you a condition for a function, and then if the function meets that condition, you'll always have an absolute maximum value and an absolute minimum value. We'll get more into this when we get to the extreme value theorem slide a little further down this lesson. But for now, I want to explain what an absolute maximum and an absolute minimum is. So the definitions here, let f be a function with domain D. If we have this set up, then f has an absolute maximum value on the domain D at point x equals c if f of x is less than or equal to f of c for all x in the domain. And similarly, f has an absolute minimum value on the domain D at point x equals c if f of c is less than or equal to f of x for all x in the domain. So this is very, very mathy. And in pictures, it might be easier to understand that if you have a function defined on some domain like this, and you pick a value c, that value is the maximum if that y value is the biggest y value on the domain D. That's what that is saying. And similarly, like I said, you can have a minimum value. Let's say you have this function and the domain goes from here to here. There's domain D. And you have this c value right here. So that is c. And the y value corresponding with that is again f of c. But now that value down here is below, it's either less than every other value or it's equal to another low value. So that's all that means, is that you have an absolute maximum if it's the highest point and you have an absolute minimum if it's the lowest point. And one other thing that you may come across is that you can use another word instead of absolute. You can say absolute maximum or minimum, or you can say global max or min, meaning it covers the entirety of the domain. So either of these words can be used and will most likely be used interchangeably. That being said, with absolute max and absolute min on the previous slide, we also have these definitions. A function f has a relative maximum at an interior point x equals c of its domain if f of x is less than or equal to f of c for all x in some open interval containing c. Now this feels a lot like the last definition of absolute maximum, and we will go over what the difference between an absolute and a relative maximum is on the next slide. But also here you can see that there's a similar definition for the relative minimum as long as you pick an x equals c that is on the interior. And one thing that I want to say about that very quickly is that when you're looking at the interior of a domain, that just means when you have, when you have a graph, and it can look like anything. Let's say it just does this. The domain runs from here A to here B. And let's call it a closed interval. We can put some closed dots here on the end. So there is the interval of the domain. And relative max and relative mins happen on the interior. So this could be a relative minimum and this could be a relative maximum. It's just we can't guarantee, in fact we cannot have a relative minimum or relative maximum being on an endpoint. So when they say an interior point, that just means it's somewhere between the endpoints of the domain. So let's take a look at what the difference between relative and absolute is. So to show the difference between what absolute and what a relative minimum and maximum are, I'm just going to draw a graph here. Something that maybe starts out here, goes up, goes way down, like this. Let's curl back down, there we go. All right. So this is a nice continuous graph. It's smooth, it's differentiable, and an absolute max and an absolute min is the highest point that the graph will ever reach. So if you look right here at this very first hump, when you follow this down to the x-axis, this C gives you the absolute maximum. This is where the absolute maximum is located. And the absolute maximum here is f of c. In fact, I'm going to call this C1 because we're going to have a lot of different examples here. So you can also see or get the idea that right here, this is the lowest the graph ever goes. So if you follow this over to the left, if I had that right, there we go. Let's call this here C2. This is where the absolute minimum is located. And the absolute minimum would be what you get if you substitute C2 into the function. But all throughout here, and I'm going to use a different color here to denote some other relative maximums, like this graph right here at this point, it tops out. It stops increasing and starts decreasing. So there's a maximum there, but it is not the highest maximum, but it is a maximum. It's only a maximum on this little part of the graph. So we call that a relative maximum. Because it's still a maximum, it's just not the biggest maximum. So the biggest maximum we call the absolute maximum. And you can see here that here's another one, here's another one, here's another one. So all of these are relative maximums because the graph stops increasing and starts decreasing at that point. It stops increasing and starts decreasing at that point. Same thing over here at this point. So on the other hand, we can have absolute and relative minimums or minima. So this point and this point and this point would all be relative minima. And that would be here, that would be here, and that would be here. And you can see that just on this little portion of the graph right here, that is, in fact, the lowest point on that little portion of the graph. So we say some open interval containing C, that value that is the minimum. So hopefully this gets you the idea that the relative maximums happen here, 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 but the biggest max is the absolute maximum. And we have some minima over here, 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 the blue and purple dots. And the lowest minimum is the absolute minimum. Now just as a side note over here to the upper right, if you have an x and y axis like this, and you look at the cubic function, y equals x cubed, something like this, this graph increases through and through, from left to right. So it never stops increasing, and as you go further left, it never stops decreasing. So here you have no max and no min. And that's great, fine and dandy that we can look here and say, well, yeah, there's an absolute maximum. Oh yeah, here's an absolute minimum. Here are some relative minima. Here are some relative maxima. And this graph has no max and no min. That's fine, except you aren't usually given a graph to identify where these relative max and mins happen or where absolute max and mins happen. So how are you supposed to find these? Well, it turns out that if you look at all of these points where the maxes and mins happen, they have one thing in common. If you draw in their tangent lines, something that looks like this all the way across, all of the relative and absolute max and mins for this example have horizontal tangent lines. So all of these tangent lines have a slope of 0. And that's very important, and that brings us to the next definition. Critical value. If f has a relative maximum or a relative minimum value at x equals c, and the derivative at that point x equals c is defined, then f prime of c equals 0. That is to say, a value of x equals c of a function of f, where the derivative at c equals 0 or the derivative at c is undefined, is a critical value of f. So essentially what we will be doing in these next few examples is trying to find out where the relative maxes and where the relative mins happen. And in order to do that, we will need to find these critical values. So we have a couple different ways of looking at it. So we have this: if f has a relative max or min at this particular point, then f prime of c equals 0. That's what I was discussing on the previous slide with the horizontal tangent lines. But what we know, how we can find these critical values, is given to us right here. We can find the critical values if we find the derivative, set it equal to 0, and solve for c. If we find the derivative and find out where it is undefined, those are where the critical values are, and where the relative maxes and relative mins could be. And with this, finally, now that we have all of this set up, what are absolute maximum and minimum definitions? What are relative maximum and minimum definitions? What is a critical value? Why they are important? We just have this final culminating topic to get through, which is the extreme value theorem. And then we can get into some examples. So let's take a look at what the extreme value theorem says. Finally, the entire reason for this section, the extreme value theorem. If f is continuous on the closed interval a to b, then f has an absolute maximum and an absolute minimum. There it is in all its glory. Great. What exactly does this mean? Well, as long as we meet the one condition that f is continuous on the closed interval, then this theorem guarantees that there will be an absolute maximum and an absolute minimum. Now, this is not the mathematical definition. This is what the theorem. This is what the theorem is in layman's terms. But this is what you will also remember. So if f is continuous on that interval, then it has an absolute max and an absolute min. And that's really, really fantastic because now we have everything we need to know. So how you will end up using the extreme value theorem, we will need to find the critical values, and then it becomes really easy after that. So as the theory over the past few slides has progressed, right, we talk about maxes and mins, we talk about finding the critical values, and then we talk about using the extreme value theorem to find the absolute max and absolute min of a function. So we'll follow the examples. In the first slide of examples, we will look at finding the absolute max and mins from a graph, and really whether or not the graphs satisfy this condition. Let's see, we will also then look at finding critical values only, and then we will go through and just use the extreme value theorem to bring all of these ideas into one type of problem. Here we go. Before we get too far into the examples, before I get too far ahead of myself, I would like to review just a couple more ideas on how to identify absolute maximum and an absolute minimum from a graph. So some graphs will pop up here in a second, and we'll give those a good looking over to find absolute maxes and absolute mins. All right, here you have 4 different graphs to look at, and we're just going to concentrate on them one by one. And what you can see here is that in this first graph, there is a closed dot in the very, very bottom of this graph. This means this graph has an absolute minimum. And as we trace this graph from left to right, it looks like it stops right there, but we cannot call that an absolute maximum because, first of all, it's an open dot, and secondly, it's not even the highest function value that we have. So we can continue going left to right, so every time we move further and further right, it's like there's a new maximum, but we have to keep going. There's a new maximum, we have to keep going. And then we end up at this open dot again. Well, let's say that that y value there is 3. What is the maximum of this graph? The absolute maximum. And some of you might say, well, it's 2.9, because 2.9 is pretty close to 3. And then I say, well, 2.99 is closer to 3, right? This open dot just means that we get as close to 3 as we can possibly get. And you say, well, I see what you're doing here, Greg. You'd say 2.999 is closer than 2.99. Well, I'll just come back and say 2.49s in a row. That's closer. So really what we end up concluding is that this is no absolute maximum. Maximum, there we go. This graph has no absolute maximum, and that's because we have this endpoint over here at the highest value of where it should be 3 is an open dot. And so we can use that logic over here. This graph has no absolute minimum, and feel free to abbreviate these, ABS-MIN, absolute minimum. And we had just stated this has no ABS maximum. No absolute minimum, no absolute maximum. So that's interesting. This graph doesn't have an absolute max, nor does it have an absolute minimum. Let's see what happens over here. It looks like this would be where the absolute minimum should happen. Let's call it -2. But there's an open dot. So that just tells us that there is no absolute minimum here. But at the top here, at the very, very top, call it 3, this is the absolute maximum here. And then with this last graph, this is the lowest point on the whole graph, call it -3. This is in fact the absolute minimum for this graph, and the absolute maximum is also a closed dot. So we have an absolute max here, call it at y = 2. So hopefully this clears up a little bit more about when graphs do and do not have absolute maxes and mins. And one more thing I want to say about all of these graphs is that none of these graphs satisfy the condition needed for the extreme value theorem. The extreme value theorem said that it has to be continuous on the closed interval. Well, this one is not continuous. This has a non-removable discontinuity here. This one is not continuous. This is also a non-removable discontinuity. This graph looks like it's continuous all the way. From left to right, you don't lift up your pencil, but it's a closed interval, meaning that these dots here would have to be closed in order for the extreme value theorem to work. And the same thing over here. This looks pretty continuous, and if it weren't for this pesky open dot over here, the extreme value theorem would also work. So since we can't say anything about the extreme value theorem because the discontinuities are here in these graphs, we are not guaranteed an absolute max or an absolute min. As you can tell in this example here, we did not have an absolute max or an absolute min, but here we did have an absolute min, but not an absolute max. So just make sure that you are checking the continuity of the entire graph, including the endpoints. Examples. Find the critical values for the following functions. Here the first function you see is y = x² minus 6x minus 7. Now in the previous slide, somewhere in the previous slides, the critical values were defined as the values that make the derivative equal 0 or where the derivative is undefined. So what you need to do then, first step, find the derivative. y prime equals 2x minus 6. Okay, here's a derivative of the original function y. And it looks like this derivative is defined everywhere. And it'll make a little more sense when we get down here to the second example what I mean by defined everywhere. There are no restrictions on the x variable in the derivative. So the only thing we can do at this point is set this derivative equal to 0 and solve this equation right here for x. So what that means is that we will have 2x minus 6 = 0. And when you solve for x, you'll end up with x equaling 3. So this is a critical value. And remember, we said critical values are where the maxes and mins happen. Well, if you go back to your college algebra or algebra 2, you may remember that you can find the vertex, the x-coordinate of a vertex of a quadratic function by using x equals -b/2a. And if you come up here and identify a as being 1, b as being -6, and c as being 7, like ax squared plus bx plus c, the standard form for a quadratic function, you can then substitute these numbers in here as being negative and -6 all over 2 times the a value is 1, which leaves you with 6/2, which is 3. So the x-coordinate for the vertex, which you should remember is either the highest or lowest point of a parabola, matches up with the critical value x equals 3. Again, the critical values tell you where the highest and lowest points happen. Okay, so that's good. So just to bring this full circle with something that you already knew, finding the x-coordinate for a vertex which is either a maximum or a minimum for a parabola. And we got the same answer when we found the derivative, set it equal to 0, and solve for x. Cool. So this works. This should give you a better feeling that this works. With this next example, we need to use the quotient rule to find the derivative. So y prime equals the denominator, x minus 2, times the derivative of the numerator, which would be 2x, minus the numerator, x squared, times the derivative of the denominator, which in this case would just be 1, all over x minus 2 squared. So the next step you want to do here is simplify the numerator. So it looks like we'll end up having 2x squared minus x squared, which will leave you with an x squared. And then in this part, we'll have minus 4x. So x squared minus 4x all over x minus 2, the quantity squared, which equals x times x minus 4 all over x minus 2, the quantity squared. So this is the derivative I want to look at, the simplified version. And so now, since we have x's in the denominator, there is a chance that the derivative could be undefined somewhere. So we will have a critical value from the denominator. So let me write this. So from denominator, x equals 2 is a critical value. And that's because if you put 2, substitute 2 in for all these x's, you will end up with a divide by 0, and that means the derivative is undefined at that value. So x equals 2 is a critical value. All right, there's one. The other way we can do this is to set this whole derivative equal to 0. And essentially what ends up happening here is that in order to make this easier to solve, you multiply both sides by x minus 2 squared, or whatever happens to be in the denominator here. So essentially what this equation boils down to is x times x minus 4 equals 0. And all of this stuff is from, in white down here, is from the numerator. So we can set each of these factors equal to 0 to see that x equals 0 and 4 are critical values. So this example, there are 3 critical values. X equals 2 because that is where the derivative is undefined, and x equals 0 and 4 where the numerator equals 0. More examples. Find the critical values for the following functions. One thing that I forgot to write here would be that we want theta to be between 0 and not including 2 pi. And anytime you're given a trig function like this, the period with which you are looking on, or the interval with which you're looking on, will be given to you. So the first thing we need to do is find the derivative. That will be y prime equals secant squared theta. So then we can use this idea that secant squared theta is really 1 over cosine squared theta to understand that this is what we will be setting equal to 0 and solving for x. In this case, solving for theta. So in the last example, we had something left over in the numerator, which we set equal to 0 and solve for x, but in this numerator here, there are no variables. So if you wanted to write this off to the side, it would look a little funny. You would have 1 equals 0, and that's false. So that doesn't give us any critical values, but we can find some critical values down here with the cosine squared of theta. So what we can do is find out where the secant squared of theta is undefined. So let's take that. Let's take the cosine squared theta equals 0. Take the square root of both sides. And if you can remember which values of theta make the cosine equal to 0, you will remember that theta equals pi over 2 and 3 pi over 2. These are the critical values for the original function here, tangent of theta. And that makes sense if you remember what the graph of the tangent of theta looks like. It starts out at 0, 0, and goes up. And there's a vertical asymptote at, you guessed it, pi over 2. And the graph starts down here again, comes up, crosses, goes up again, and another vertical asymptote at 3 pi over 2. And when you find the derivative of the tangent of theta, those vertical asymptotes are still there. So that's why these critical values here, pi over 2 and 3 pi over 2, are critical values, but it is where the function or where the derivative is not defined, not where the derivative equals 0. All right, so in the next example here, there is this fraction y equals x over x squared plus 1. So y prime will be the denominator, x squared plus 1, times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And then to simplify this down, this will be done very similarly to the second example on the last slide. There's an x squared minus 2x squared. This will leave you with a negative x squared plus 1 all over x squared plus 1, the quantity squared. And if you want to get really fancy about it, you can common factor out a negative in the numerator and leave this as x squared plus 1, the quantity squared, and then you can even factor that, so negative x plus 1, x minus 1 all over x squared plus 1 squared. So this will be the derivative that I use. And the last time there was a fraction on the previous slide, not this one here. Even this one here, we had to take the denominator, set it equal to 0, and solve for x. So I'm going to do that right over here. I'm going to write denominator to let me know where the derivative is undefined. And so that is x squared plus 1 squared equals 0. So my first step here will be this 2 square root both sides, x squared plus 1 equals 0. My next step is to subtract 1, so that means x squared equals negative 1. My next step is to square root again, so I can isolate x, and that tells me x equals plus or minus I. And that's no good. We cannot have imaginary numbers be critical values. Seeing as how we are headed toward graphing more complex functions in a few lessons, there's no place to graph imaginary numbers. So we don't get any critical values from the denominator. So we have to check for the numerator then. So over here in white, I'm going to write numerator. And the numerator is negative x plus 1 times x minus 1. and we'll set that equal to 0. Essentially, again, why we can set the numerator equal to 0 to find critical values is because way over here, if you set the entire fraction equal to 0 and multiply by the denominator, 0 times the denominator here will be equal to that numerator. So it's just the numerator equaling 0. So when you solve these for x, you'll get x equals 1 and negative 1. And these are the critical values for this function. And that's because when you substitute these numbers into the derivative, you'll end up getting 0. In this example, finally we get to finding the absolute max and absolute min for the following function on the given interval. Now, in order to find the absolute max and absolute min, we will need to use the extreme value theorem. And if you look at this function here, I promise you that this is in fact a continuous function on this interval. The reason I can tell you that is, well, I guess I can prove it to you. If you square out this binomial by you'll end up with x squared plus 6x plus 9, all of that multiplied by 1/2, and then over here minus 4. And so when you distribute the 1/2 and combine the 1/2 times 9 and then subtract 4 from it, you end up with plus 1/2. This is a polynomial. And polynomials are continuous on all of the real numbers. So if a polynomial is continuous on all of the real numbers, then it is definitely continuous on this little interval right here. Now, we have a function here, and you can use either version. You will get the derivative for either, because the first step that you need to do for finding the absolute max and the absolute minimum is find the critical values. So when you look at this, we can see that the critical values for this will be, let's see, first we have to take the derivative. So f prime of x will equal x plus 3. Yeah, that's it, x plus 3. And if you set that equal to 0, x plus 3 equals 0, and you solve for x, that means x equals negative 3. So there's a critical value. And just by taking a quick look at the derivative, you can see that the derivative is defined everywhere. There's no denominator, there's no trig function, there's no absolute value. It is defined everywhere. So what that means is that if it is defined everywhere, then it's defined on the small interval that's given to you, which is what we're really concentrating on. More on that in the next example. So finding the critical values, there it is. This is the only critical value we will have. Next, and this is the hard part, we have to evaluate f of x at all critical values and endpoints. So what does that mean? We have to evaluate f of negative 3. There's the critical value. We have to evaluate f of negative 5. That is the left endpoint of our interval. And we have to evaluate f of 1. So these are end points. So f of negative 3, Well, all we have to do is substitute this -3 in here for x. You will end up with -4. Similarly, you can substitute -5 in here for this x, or even down here for these x's. This is the multiplied out version of this. And you'll end up with -2. And over here with the last one, you'll end up with 4. So that's it. Evaluate all of those things. The very last step is to interpret your answers. It really is as easy as saying -4 is the smallest number we got. So this is the absolute minimum. +4 is the biggest number you got. So this is the absolute maximum. That easy. But we're going to word it in such a way that it is what I just said. So showing this is not enough. You want to write it out in words. Writing in math. I know. You have to be able to interpret and communicate your answers sometimes. So this is one of those times. We can say the absolute minimum value is -4. That is the actual minimum value. And that happens at x equals -3. So -3 is where the absolute minimum value happens. In the other one here, the absolute maximum value is +4. So the absolute maximum value is 4, and this happens at x equals +1. Now I want to run through this same example on the next slide, but just with a couple different intervals, just to give you all an idea of how intervals can affect the process with using the extreme value theorem. All right, so here's the same exact function, and we already know what the critical value is for this function. But now I have two different intervals over here that I want to investigate what happens when we have these different intervals. So you can see that with this first interval, right, we found the critical value. The second step is to evaluate f at the end points and the critical value. Now this is where it gets just a little bit interesting, because on the interval 2, 5, -3 isn't in there. -3 is not on the interval, so we cannot use the critical value if the interval does not contain the critical value. Let this be a lesson learned before you learn your lesson in homework. So since 3 isn't in that interval, we don't use it. We get rid of it, and in fact we can only evaluate at the endpoints. So we need to figure out what is f of 2 and what is f of 5. So here is what you get when you substitute 2 in for x and 5 in for x. You get 17 halves for 2 and 28 for 5. And then we can just go through and write down the conclusions again. So then here are the interpreted answers, being that the absolute minimum is 17/2, and that happens at x equals 2, that is a period. and the absolute maximum is 28 and happens at x equals 5. And I don't think that's much of a shocker for anybody out there that 28 is bigger than 17 over 2. All right, so there's that one. And with this other one over here in this light blue color, the second step is to evaluate f at the endpoints in the critical values, so same step. And yes, this critical value is in the interval, so we will need to find f of -7, f of -3, and f of 1. So we can do that, and we get 4, -4, and 4 respectively. So we know that this is the absolute minimum because that's the smallest value. And what? Oh my goodness, we have a 4 and a 4. We have two 4s. So does that mean the absolute maximum doesn't exist? That there isn't one? No, what this means is that there are two absolute maximums. So we can write. We have an absolute min is, what is it, -4, and happens at x equals -3. And in fact, the absolute max is +4 and happens at x equals -7 and 1. So you just list these two numbers out right here like this, -7 and 1, because there are two x values that give you the same absolute maximum. One more example. And one more example here. Determine the absolute extreme values of f on the given interval. So you can see that we have this function f of x equals 10x over 4 minus x squared on the interval 3 to 6. Now again, the first thing that we need to do here in order to use the extreme value theorem is to ask this question: is f of x continuous on the interval 3 to 6? And in the previous example, I just sort of talked my way through it. Well, where this function is not continuous is where the denominator equals 0. So there's 4 minus x squared equals 0. You can add x squared to both sides to get 4 equals x squared. And then you can take the square root and get x equals plus or minus 2. And these are vertical asymptotes at x equals +2 and x equals -2. But neither of these are in the interval. So as far as this interval is concerned, yes, this function is continuous. If you are looking at the entire x-axis, no, this function is not continuous. It's discontinuous here. But since we are not looking at the entire x-axis, just this little piece, it is continuous. So we are able to use the extreme value theorem here. That being said, let's find the derivative so we can find the critical values. So step 1, critical values. That requires, as I just mentioned, finding the derivative. So f prime of x is the denominator, 4 minus x squared, times the derivative of the numerator, which is 10, minus the numerator, which is 10x, times the derivative of the denominator, which is -2x, all over the denominator squared. So 4 minus x squared, the quantity squared. And if you go through and you simplify this numerator as best you can, you will end up with 40 plus 10x squared over 4 minus x squared, the quantity squared. This, now we can set the numerator equal to 0 and we can set the denominator equal to 0. We've already set the denominator equal to 0 and we got these two values. So really quickly I'm going to start a list. Critical values. And with these critical values, we know positive 2 and negative 2 will be a part of that list. Maybe. We'll get into that in just a second. And then if you set the top equal to 0 and solve for x, you'll get that x equals plus or minus 2i. And again, we don't have any room for i's in this situation. In these exercises. So i's don't work. And as a matter of fact, these two critical values aren't on the interval, right? We mentioned that already. So negative 2 is not in this interval, and neither is positive 2. So there are no critical values for this whole entire function. Okay, so what we do now is we evaluate f at the critical values and the endpoints. And in this situation, we're just evaluating f of 3 and f of 6 because we don't have any critical values. We only have these two endpoints. So when you evaluate both of these, you end up with these two values right here. And then we can go through and say here that this is the absolute max and that this one is the absolute min. And then we can go ahead and finish writing our statements that the absolute minimum is negative 6 and happens at x equals 3. And also we can say the absolute maximum is negative 15 over 8 and happens at x equals 6. So here are where the absolute mins and the absolute maxes happen.